This is lesson 3 of Precalculus. Today we're talking about transformations of functions from section 1.3 in the college algebra textbook. What are transformations? We're referring here to starting with a graph of a given or a parent function and making changes to that graph as required to obtain a graph that represents a slightly different formula. We'll begin here with vertical shifts. These are transformations that move a graph up or down. And we begin with being given the graph of y equals f of x. From this graph, we want to plot a graph of y equals f of x plus 4. So what we're going to do here is we're going to add 4 to each of the y coordinates on the original graph. So we add 4 to the y coordinates of y equals f of x. We end up with the graph that I've already plotted here, but let me show you exactly what we've done. We've taken each of these points, these corner points of such, like the point 2, 1. We've left 2 as our x-coordinate and added 4 to the y-coordinate of 1 here to obtain the point 2, 5. For the point, what have we got here? 1, 2, 3, 4. We have negative 4, negative 2. We added 2 to that, we added 4 to that y-coordinate of negative 2 to bring us to the point negative 4, 2, and so forth. So we've essentially shifted the graph of y equals f of x up by 4 units. Notice that vertical shifts such as this affect the output values of f of x. So here we take f of x and we add 4 to that output value of f of x. If instead of f of x plus 4, say we were graphing here y equals f of x minus 3, we would simply move the graph down by 3 units. Move each point on the graph down by 3 units, like so. And that would give us the graph of y equals f of x minus 3. Next, we'll look at horizontal shifts. These are transformations that move a graph left or right. We're starting by graphing the function f of x equals square root of x minus 3. And note that the parent function, square root of x, would be the closest to this function that we could find, where we could do a simple transformation of y equals square root of x to obtain a graph of f of x equals square root of x minus 3. What we're going to do here is we're going to add 3 to the x coordinates. In the previous example, the plus 4 was out of the square root sign. Here the minus 3 is, or that the plus 4 was outside of the original f of x function. Here the minus 3 is inside the square root, inside the original function of square root of x. And so we're adding 3 to the x coordinates here. We'll end up with a graph that looks like such. Let's look at a couple of these points. We have the point 4, 2. We simply added 3 to the x coordinate of 4 to give us the point 7, 2. The point 0, 0, we added 3 to that x coordinate of 0 to give us the point 3, 0, and so forth. So essentially what we've done, we've taken the graph y equals square root of x, we've shifted that graph to the right by 3 units, so now we have y equals square root of x minus 3. Okay, horizontal shifts affect the input values to y equals square root of x. So if we have the x minus 3, this affects the input value of x. And so when we're affecting the input value to a function, this is going to affect the graph somehow horizontally, and that's what we've done here. Let's just check to make sure that this actually works as it should. Let's take this x value of 7, and if x equals 7 here, then y is going to equal the square root. According to our function, y would equal the square root of 7 minus 3 or square root of 4, and that does indeed give us the 2. So we can see this works. Instead of square root of x minus 3, what if I had the, say, I wanted to graph y equals the square root of x plus 2. What this is going to do, rather than shift the graph to the right, this would shift the original graph to the left by 2 units. So everything here would move left by 2 units. And something like so. So this would be the graph of y equals square root of x plus 2. Okay, let's move on to vertical reflections. These are transformations that reflect a graph across the x-axis. And let's begin with sketching the graph of the function f of x equals negative square root x. We can see that we want to again start with the parent function, y equals square root x here. And to graph this function, the negative is outside of the square root sign, which means we're affecting things vertically. So what we're going to do to go from square root of x to negative square root of x, we're going to multiply the y coordinates by negative 1. And we have a graph that looks like so. What we did, for example, we took the point on our original graph 4, 2. We multiplied the 2 by negative 1 to give us the point 4, negative 2 on our graph of y equals negative square root x. And this is a rigid transformation, as the previous 2 examples have been. A rigid transformation does not change the shape of the original graph. It just moves it in some way. Okay, so let's move on to look at horizontal reflections, which are transformations that reflect a graph across the x-axis. Here we're going to graph f of x equals square root of negative x. Again, we'll start with y equals square root x. But the negative being inside the square root sign is going to affect the x values of the graph, or it's going to affect the graph horizontally rather than vertically. So what we're going to do here is we're going to look at our original x coordinates of the points on the graph, and we're going to multiply the x coordinates by negative 1. So we end up with a graph that looks like so. For example, we took the point on our original graph 1, 1. We multiplied that x coordinate of 1 by negative 1 to give us a point negative 1, 1. And we have the graph y equals square root of negative x. Okay. Let's move on to vertical scalings. These are transformations that stretch or compress a graph in the vertical direction. And the first one we have is f of x equals 3 times the square root of x. Again, we'll start with the parent function, y equals square root x. We're affecting the output to the function. And so what we're going to do here is we're going to multiply the y coordinates of our original graph by 3, and we end up with a graph that looks like so. And you can see this is not a rigid graph. The shape of our transformed graph is quite different than the original graph. This is y equals 3 square root x. Let's just look at a couple of points on here. We started with the point 4, 2. We left the x coordinate as it was. We multiplied that y coordinate of 2 by 3, so this becomes the point on our new graph of 4, 6. The point 0, 0 would stay the same, right? Multiplying 0 by 3 is still 0. The original point 1, 1, multiplying that y coordinate by 3 gives us a new point 1, 3. Okay, so what if instead, this is a vertical stretch. You can see the graph stretches in the vertical direction. Sometimes we say by a factor of 3. What if instead of 3 square root of x, say we wanted to graph y equals 1/2 square root x. So in this case, we would just multiply each of the y coordinates on the original graph by 1/2. We'd still have 0, 0. We'd have 1, 1/2. We'd have 4, 1. And then we'd just connect those dots with a nice little curve there. And this would give us a graph of y equals 1/2 square root of x. So let's move on to horizontal scalings. These are transformations that stretch or compress a graph in the horizontal direction. And I want to go back here just a minute. This graph of y equals 1/2 square root of x, we say that compresses the original graph of y equals square root of x in the horizontal or in the vertical direction. Now we're going to be working in the horizontal direction. So we're looking at transformations that stretch or compress a graph in the horizontal direction. And we begin with f of x equals square root of 1/2 x. We'll again use y equals square root of x as our parent function here. And notice that 1/2 affects the input to our function square root of x. And so this is going to affect the x coordinates of the original graph. What we're going to do here is we're going to multiply our x coordinates by, and here's the trick here. So when we were shifting things left and right, say I was graphing the square root of x minus 3, looks to me like I should move things left by 3, but it's always the opposite when we're doing things in the horizontal direction. So with square root of x minus 3, we move things to the right. Here, I'm thinking, well, I want to probably multiply the x coordinates by 1/2, but no, in the horizontal direction, things are usually opposite of what you'd think. So we actually are multiplying the x coordinates by 1 over 1/2, or 2. We end up with the graph y equals square root of 1/2 x right here. And so let's see what we did. Say we started with the point here 4, 2. We multiplied that x coordinate of 4 by 2 to give us the new point on our graph of 4, 2, of 8, 2. Our point on the graph of y equals square root of 1/2 x of 8, 2. If we started with the point 1, 1, that becomes the point 2, 1, multiplying the x coordinate by 2 there, and 0, 0 would stay the same. So this is what we would call a horizontal stretch. If I want to look at a horizontal compression, let's just do an example there. We'll try this. Say I want to graph y equals the square root of 3x. So what this is going to do is it's going to take each of those x coordinates on our original graph, and we're going to multiply the x coordinates by 1/3. And so instead of the point 1, 3, we would have the point 1/3. And instead of the, okay, so let me say it again. Instead of the point 1, 1, we would have the point 1/3, 1. Instead of the point 4, 2, we would have the point 4/3, 2. So this is what it would look like to have a graph that is compressed in the horizontal direction. And again, this is a non-rigid transformation. The shape of our new graphs is different than the shape of the original graph. Okay, moving on to combinations of transformations. We start by using the graph that we're given here of y equals f of x to graph y equals -2 f of x plus 3 minus 4. And I like to go in a particular order here just to make sure I don't make mistakes, because sometimes you can undo things in the wrong way if you go in the wrong order, which we'll see in one example later on. So I'm going to start inside my function here. I'm going to start as close as I can to the x. So I'm going to look at the x plus 3. What does that plus 3 do to my original graph of y equals f of x? Well, if you remember what we've been doing, this would cause a shift to the left of all the points on the graph. We're going to go left by 3 units. In other words, we're going to take each of our original x coordinates and we're going to subtract 3 from those x coordinates. So the point 2, 1 would transform over to become the point negative 1, 1. And this would give us the graph. This would be y equals f of x plus 3. And then we'll keep working on this till we get to the plot that we want. So we started inside the parentheses here with x plus 3 to give us the graph of y equals f of x plus 3. And now we're going to stay as close as we can to that function. We're going to grab this 2 next. What this 2 is going to do is it's going to stretch in the vertical direction, our graph. So we're going to basically multiply the y coordinates of our graph by 2. And we'll get the graph here. So for example, let's take the point 1, negative 3. Multiplying that y coordinate by 2 would give us a point on our new graph of 1, negative 6, and so forth. Now, if we gave this graph a name, the function associated with a name, it would be y equals 2 f of x plus 3. And we'll move on. So this is y equals 2 f of x plus 3. So what do we want to do next? Let's grab this negative. We know this negative is going to reflect the graph across the x-axis. And to do that, we multiply we multiply the y coordinates by negative 1 to give us this graph, which is going to be y equals negative 2 f of x plus 3. For an example of what we did, let's just look at this point 1, negative 6. Multiplying that value of negative 6 by negative 1 would give us the new point on our graph, 1, 6. And if you were doing this on your own, you'd want to work with each of these corner points here. Okay, and so we have y equals negative 2 f of x plus 3. The next thing we want to do is we only have one number here left to take care of, minus 4. This is the number that's going to shift our graph down by 4 units. So to do that, we're going to add negative 4 to the y coordinates here. And our new graph will look like so. For example, we took the point 1, 6. We subtracted 4 from the 6 to give us the point 1, 2. And now we have finally the graph y equals negative 2 f of x plus 3 minus 4. Okay, moving on. Graphing transformations of a function f. This is a set of steps here, for graphing transformations. We did just fine on the graph that we just did when we have a combination of transformations to do. But sometimes these steps here are very helpful. If we look at our function as being that we want to graph as being y equals a f of bx minus c plus d, if we can identify a, b, c, and d, the first step here is to add c to each x coordinate on the original graph of y equals f of x. Secondly, we multiply the x coordinates of the graph obtained in step 1 by 1 over b. Thirdly, we multiply the y-coordinates of the graph obtained in step 2 by A, and then last we would add D to the y-coordinates of the graph obtained in step 3. And going through these steps actually takes care of reflections as well in steps 2 and 3, so we don't need to mess with reflections separately here. Well, let's do an example where we use these steps. We're going to sketch a graph of the function f of x equals negative x minus 3 squared plus 2. And here you can see the parent function we want to use is y equals x squared. I've made dots on the points that I use for transformations of this function. Negative 2, 4, negative 1, 1, 0, 0, 1, 1, and 4, 2. And from here, we're going to look for what is, so remember our guide that we were given here, y equals a f of bx minus c, and then plus d. Let's identify a, b, c, and d here. Well, a would be equal to negative 1. B would be equal to 1 here. C would be 3. And D would be equal to 2. So once we've identified these values for A, B, C, and D, let's go ahead and look at the first step here is to add C to each of the x-coordinates of the graph of y equals f of x. So we want to add 3 to each of the x-coordinates here. So if we add 3 to the x-coordinates, we obtain this green graph over here. This would actually be the graph y equals x minus 3 squared. Let's just look at one point here. The point may be 2, 4. If I added 3 to the x-coordinate on that graph, we would have the point 5, 4. Okay, so we got that. And then we're going to move on to our next step here. So right now we have the graph of y equals x minus 3 squared. Okay, so we took care of C. Step 2 here is to work with B. Well, in this case, B equals 1. So there's no change to the graph from the value of B here. So no change indicated by the value for B. And we then next move on to A. So here A was equal to negative 1. A comes from the negative out front here. So what does A tell us to do? So A tells us to multiply the y-coordinates of our original graph here, or the graph obtained previously. We want to multiply the y-coordinates by negative 1. And you can see what that's going to do to this graph. It's going to reflect it across the x-axis. For example, let's look at this point 1, 4. If I multiply the y-coordinate of 4 by negative 1, we would get this new point on our graph of 1, negative 4. And now, if I give this graph a name, it would be y equals negative x minus 3 squared. And we'll move on to the next step. So in the next step, we start with y equals negative x minus 3 squared. And if you remember, we found that D was equal to 2 here. So what do I do with D? I add D to the y coordinates of the graph I obtained in the previous step. So I'm going to add 2 to the y coordinates. And we'll end up with this graph. Let's just look at one y-coordinate here. Well, 1 point on our original graph here. 3, 0. If I add 2 to the y-coordinate of 0 there, I end up with a point on our new graph of 3, 2. And finally, we have the graph here of y equals f of x, or y equals negative x minus 3 squared plus 2. All right, so let's move on. We could have actually completed this transformation by using we didn't really need the chart for this so much because we could have done this the way we did the previous problem. But this next example is one where I have two different things going on under my square root sign. It's very helpful to follow those steps. So let's work through this problem next. So I have g of x equals square root of 2x plus 4. You can see we want to start again with a graph of y equals square root of x as our parent function here. And before I go any further, I'm going to look at my function g and determine what a, b, c, and d are. So here a is the number. Well, what we're looking for is where y equals a f of bx minus c plus d. So you can see here that a is equal to 0. And you can see that actually here at the end d is equal to 0. Oh, I'm sorry, a is not equal to 0. That would be bad. Let's start over there. So in fact, I'm going to use a little bit different color here to make it easier to see. So here a is equal to 1, or we would only have g of x equals 0, right? And d equals 0. So both of these values for a and d, however, are not going to change our graph of y equals square root of x. There's no change caused by these two values. What we are interested in here is we can see that b equals 2. And we can see that c, what's c going to be equal to here? Oh, sorry about that. C, we have 2x plus 4. That's 2x minus a negative 4. And so c would be equal to negative 4 here. Okay, so according to our orders, the very first number that we want to mess with is c, according to our steps for transforming functions. And so if c equals negative 4, I'm going to work with that number first. What do we do with c? Well, c equals negative 4 tells us that we need to add negative 4 to the x-coordinates of our original graph. And if we do that, here's our new graph that we get from that. So, for example, we started with the point on our original graph, 0, 0. That moved to the left 4 units. We added 4 to the x-coordinate there to give us the new point, negative 4, 0. For 4, 2, we added negative 4 to that x-coordinate to give us the new point, 0, 2. And 1, 1 becomes negative 3, 1. Okay, so now if we wrote what this function is, it's square root of x plus 4. And let's move on to the second step in solving this problem and creating our final graph. Right now we have y equals square root of x plus 4. And I want to do something with this 2 here. Well, we found that actually b is equal to 2 in this example. And if we use the steps, what do we do with b? Well, remember, b tells us that we need to multiply the x-coordinates by 1 over b. So in this case, we're going to be multiplying the x-coordinates of our previous graph by 1 over 2, or 1/2. That's going to give us our resulting blue graph here. This would be y equals g of x, or y equals square root of 2x plus 4. But let's just check a couple points here to make sure we did this right. So the point negative 4, 0, we multiplied that x-coordinate of negative 4 by 1/2, which would give us negative 2, 0. That looks right. And negative 3, 1, we multiplied negative 3 by 1/2 to give us negative 3/2. 1. The point 0, 2, we multiplied 0 by 1/2, and that is still 0, so we still have the point 0, 2 here. So this is a horizontal compression, and it gives us our final graph of y equals square root of 2x plus 4. And it's really confusing if you do this in a different order. So I would try, if you want to mess around with this, try it. But if I have a coefficient, a non-1 coefficient on x here, and I have a non-zero number added underneath the square root sign or within any input to a function that I'm working with, it's very much easier to follow these steps that we've done here in this order, because this can be way confusing. Okay, let's go on and try on your own the very first one for today. Sketch a graph of the function f of x equals 2 times the square root of x plus 3 plus 4. I have one more thing I want to try before I send you off on your own. This is where we're going to let f of x equal the square root of x, and we're going to find a function g whose graph is obtained from f after the following sequence of transformations. The first thing we want to do to f of x equals square root of x is we want to shift its graph to the right by 5 units. The corresponding function we would use to do that would be this y equals the square root of shifting the right 5 units. We'd think, well, would that be x plus 5? No, it's x minus 5. Remember, right and left is the opposite of what you'd expect. So from step 1, we're going to use a result to move on to step 2. Then vertically stretching by a factor of 3 means we want to take 3 times the square root of x minus 5. Okay, so in step 2, we obtain y equals 3 times the square root of x minus 5. In step 4, we shift the graph of this function down by 4 units, which means we're going to have y equals 3 square root of x minus 5 and then minus 4. And our last step here is to reflect about the x-axis. So we're going to multiply our entire, here we're reflecting our entire function about the x-axis. I'm going to put a negative in front of some parentheses that enclose 3 square root of x minus 5 minus 4. When I distribute that negative through, I'll have my resulting function g of x that we're looking for. G of x is going to equal negative 3 square root of x minus 5 plus 4. And we have it. And that leads us to the final try on your own, number 2 here. Let f of x equal absolute value of x. Find a function g whose graph is obtained from f after the following sequence of transformations. Show the function in each step along the way and continue steps 2, 3, and 4 from the function obtained in the previous step. Number 1, shift left 3 units. 2, vertically stretch by a factor of 2. 3, reflect about the x-axis. 4, shift down 1 unit. So please let me know if you have any questions about this assignment, and I hope you have fun with graphing.